In the previous video, we explored how to use the online obfuscator shifting codes and learned about obfuscation primitives. Now, let's take it a step further by compiling the code and attempting to reverse engineer it. In this video, you'll dive into the concept of side-channel attacks and gain hands-on experience. We'll use instruction counts as a metric to analyze program execution and leverage it to our advantage. Additionally, we'll utilize Dumpulator to emulate obfuscated code and brute force the program's password. Let's begin by creating a simple program that checks a password. The program contains a predefined password string, which is compared with the password provided via command line arguments. The mystrcmpi function serves as our custom implementation of the strcmp function. We avoid using the standard library to bypass external calls and XMM comparison instructions. It's worth noting the unique behavior of the mystrcmpi function. Each character comparison requires exactly one loop iteration. This means the number of iterations scales with the length of the string. We now obfuscate the code using shifting dot codes with all obfuscation passes enabled. Afterward, download the output bitcode file and save it with a .ll extension. To compile it, we're going to need Clang. I'll choose Windows Platform because I know you like it. So on Windows, you'd need Visual Studio or Visual Studio Build Tools. You could freely download Visual Studio Community Edition from Microsoft. When installing it, make sure to install C++, Build Tools and Clang. After the installation, bring up the console by clicking on x64 Native Tools command prompt for VS 2022 in the Start menu. Type the command on the screen to compile the code. Add the -G flag to get debug symbols if you want. Note, we're using the -O0 flag to disable optimizations. This is important because otherwise the optimizing compiler will remove some obfuscation techniques. Currently, there are no annotations added by shifting dot codes to prevent this. Now we have the .exe file. Try to run it, verify the command line arguments, and test some passwords. Let's open it in the disassembler, or a decompiler of your choice. You won't see anything meaningful in it, let alone the password. And the code graph? It should be flattened, if you remember our previous video. So, the big question is, how do we get the password? This is where the magic of a side-channel attack comes in. Since we have written the code ourselves, we know that the bigger the instruction count, the longer the code is executed, the more likely it is that we've hit the correct code. Simple observation, right? So, let's run the code and measure the instruction count. It's worth mentioning that quality CTF challenges go through a QA stage. These kinds of attacks are usually prevented, so don't expect too much out of that. That being said, you can still find side-channel attacks quite useful. Since we're on Windows, let's embrace Windows tooling. x64 Debug. It's an awesome open-source debugger maintained by just one person. Consider donating to support his incredible work. Once you've loaded the .x file into x64dbg, add the password to the command line arguments. Run the program until the main function is called. It should be pretty straightforward to find the main function. If you struggle at this point, use symbols to help you. Once you reach the main function at runtime, make a dump with the minidump command. In the program's memory, the password command line argument is located at the RGV pointer array at index 1. The RGV array itself is located at the RDX register. Let's write a script in Python that uses Dumpulator, another open-source project by the same author, to brute force the command line code and measure the instruction count. First, you need Python installed. Then, you can install Dumpulator using pip. Let's get started with the simple script which just prints you a trace of emulation. Call Dumpulator with the path to the dump. Enable trace flag. Then call the start method with the RIP register value. Now call the script and check the output. You should see "you lose" message. Remember, we just used password as a command line argument. That is not the correct one. Also, you should get a trace file. Each assembly instruction is logged. Scroll it until you find the first call instruction. The destination of that call is the print function. Copy its address. We'll use it later as a signal to stop the emulation. Now you're ready to write a final script. Let's break it down. You create a Dumpulator instance. Now, without a trace flag, you set variables, registers which are going to reset at every emulation iteration. To measure the instruction count, you'll install Unicorn Hook. Dumpulator relies on Unicorn behind the scenes, with a counter as a parameter. Try password function is responsible to kick off the iteration. It returns instruction count and string passed to print function. Brute force password function actually updates password one character at a time and calls try password function. It saves the character if instruction count is bigger than previous. This is how we know that we've hit the correct character. It also stops if print function is called with anything but "you lose" message. Now let's finally run the script. It'll take a moment to run, but you should see the progress, and eventually the correct password. If something is wrong, don't worry. Use ChatGPT or Cursor to help you out. Use the trace flag to debug the emulation step by step. If it still fails, just shoot a comment, I'll help you out. That's a wrap. You've just learned to obfuscate code with shifting dot codes. Make a runtime dump at the entry point. Use a side channel attack to measure the instruction count. Finally, run emulation with Dumpulator, brute forcing the command line password. I hope you've enjoyed the video. Feel free to propose a subject for the next one.